Hi, welcome to this webinar on real-time feature pipelines with Hopsworks. My name is Jim Dowling. I'm CEO and co-founder of Hopsworks, and I'm going to introduce this topic of real-time feature pipelines in the context of what we call real-time machine learning. And real-time machine learning is really the highest end of business value that you can create with AI. It's about building systems that can use signals from the environment, can use new data points to make changing predictions based on whatever's happening in the environment. So whether you're building an online fraud detection system that can adapt very quickly to changes in fraud patterns, or a network intrusion detection system, or maybe you're building a recommendation system, you might think of something like TikTok, which reacts very quickly to changes in your in the content that you view. So as you view content in TikTok, many of you will notice that it's able to adapt very quickly to the changes in the content that you consume. So if you tend to consume a lot of sports videos, it will tend to recommend more sports videos for you. Many people think this is because they're training models in real time. No, they're changing the data that's used to make the predictions at very low latency. And that's called features. And this is really about creating the freshest features, the features with the lowest latency from when you swipe that video to when that data is available to make a prediction. If TikTok knows that you looked at some sports videos in the last few seconds, within a few seconds, it's able to then make those predictions to say, well, I think you're now currently interested in sports. And if you change the types of videos you look at, it can quickly adapt to that. So it's about building infrastructure to enable you to build these type of real-time adaptive machine learning systems. Now, today, we're going to talk primarily about what we call real-time feature pipelines. And what this is really about is how do we get the real-time data from where it's generated, turn it into features, compute features with that data, and make those features available through a feature store, in our case, the Hopsworks feature store, so that the real-time applications or online applications can make changing predictions based on this new data or new features that are available to them. So where AI comes into the picture is primarily companies will have their data under management. And if we have a look at the diagram here, we can see that most companies who engage in AI have their data under management. They've done some business intelligence to extract data value from their data. Maybe you're doing historical analysis of your data. When you get into machine learning, you'll often start by looking at what we call analytical machine learning systems, where we can make batch predictions on batches of data, which can be very useful. And we're going to talk today primarily at the highest value case here. So without further ado, let's get into the topic. I'm going to start by talking about the Hopsworks feature store, because this is where we store the features that are going to be consumed by our online applications. So this is the target of our online feature pipelines, so the real-time feature pipelines that we're talking about. So what we're going to look at is how do we get the data into the feature store? This is a streaming API for real-time features. And then we have a batch API for higher bandwidth, higher latency features that get written in. Now in Hopsworks, we represent tables of features in what we call feature groups. So these can be stored inside the platform, but if you have your features already in tables in Snowflake or Redshift or BigQuery, you can mount them directly in as what we call external feature groups in the platform. So this offline feature store, it can be any data warehouse you want, or it can be stored as hoodie tables in Hopsworks. The features that are going to be served in real time via what we call the online API, so they're going to be served at very low latency to these online applications. They're stored internally in a platform in Hopsworks called RonDB. It's a fork of NDB cluster, a storage engine from MySQL developed by us at Hopsworks. And then for the data that's served offline, so if you're going to create training data or batch data for scoring, that comes via the offline API, which, as we said, can pull the data from a data warehouse, external data warehouse, or from Hopsworks itself. So these are the core concepts we're going to build around, that the data can be written either in batch or in streaming to the feature store, and then it can be read at either low latency individual rows of features, what we call feature vectors, or batches of features in data frames or files. So let's look at how this fits into the bigger picture. So the bigger picture of real-time machine learning is that it's not just the case that you have data in a data warehouse. So much data will be collected in a data warehouse as a single source of truth for analytics for companies. But when we want to do real-time machine learning, we'll also need to plug in the applications that are generating real-time data into a higher performance system that can get the data to the feature store faster. And typically that's what's highlighted in here in red, called the event bus. So an event bus could be a platform like Kinesis or Kafka, and applications and services that generate data can push data to event buses. From there, we'll look at streaming pipelines, so these real-time feature computation platforms to push the features in real time to the feature store, to these feature groups. And from there, the data will be extracted and used by, in the case of real-time machine learning, primarily online applications. Of course, the feature store has also offline API for batch consumption of features, for training, and also for batch serving of applications. So a little bit more detail on the feature pipelines and how the features are used in training pipelines. Because remember, the feature store isn't really just about these feature pipelines. Feature pipelines are used to create the features, and the feature pipelines that feed the feature store typically, you can say that they contain what we call model-independent transformations. So the kind of things that we might do is we might aggregate data from our data lake or data warehouse or an external database, or even from an event bus like Kafka. We'll compute things like bins of features, feature crosses. We might compute embeddings. These are what we call model-independent transformations, because the features that we create can be used potentially across many different models. And that's one of the core principles of a feature store, is that we like features to be reused across models. Now, once the features are available in the feature store, you will obviously want to use those features to create models. That means training models. So training models typically requires a training pipeline. We're not going to talk too much about it today. And the output of your training pipeline is a model. And some of the steps you'll have here is model-specific transformations, maybe one-hot encoding or normalizing numerical features, training the models and evaluating them. Now, the reason why it's important to have a feature store in this case is that the feature store will help prevent what we call training serving skew or training inference skew, because we're computing the features once in this feature pipeline, and we're using them for training here. And we'll see on a subsequent slide that we'll use the same features when we're doing inference. So in the real-time case, we'll need these streaming feature pipelines to write the features with low latency to the feature store. And then we'll have an inference pipeline that'll pull them out with low latency and feed them to the online applications. I mentioned that features should be reusable. And the benefit of this is that the number of models that you can create becomes independent of the number of feature pipelines when you have reusable features. So that's why we have model-specific transformations outside of the feature store. This means that each model can have its own different transformations for the features, and the features can be reused across more models. Okay, so the feature pipelines, as we said, can be either batch pipelines or streaming feature pipelines. On the other side, when we want to consume the features for scoring, we have what's called an inference pipeline. Now, today we're going to talk primarily about online inference pipelines. You also have batch inference pipelines. But the online inference pipelines, they'll typically retrieve the pre-computed features in the feature store, again with low latency. They may or may not apply model-specific transformations. If you're in a use case where you have really low latency requirements, you might, in that case, not worry so much about storing the features in an untransformed state. So you can normalize those numerical features before you write them. They won't be particularly reusable because, for example, in a classical feature story, you might want to say, well, I'd like to create training data between these time ranges, and any features you've stored normalized can only be used in the time range across which they've been normalized. So often, if you're in a very low latency scenario, you might write to feature groups that store normalized features, and they're just used specifically for inference. And you might have a separate pipeline then to create untransformed features that can be reused in different models. But in this case, the inference pipelines can, if they don't have latency sensitivity requirements, model-specific transformations. There may be some features that you can only compute on demand. So it may be that some data comes in from the application and we need to compute a feature from it, and it's not available pre-computed in the feature store. We'll look at that later on as well. And then finally, of course, an inference pipeline needs to make a prediction. So it's taking the data from the feature store, the pre-computed features, potentially any input data to look up those features, and also any input data for what we call on-demand features. Together, they're all going to be put together into a feature vector that will make a prediction on the model with. And then that prediction will be returned to the application in the online case. The application will use that prediction to do something intelligent. Now, let's look at how this fits into the bigger picture of feature stores. We talked about feature pipelines. Now, many of you who have taken courses on machine learning will be aware of what we call the machine learning pipeline. Now, the feature store breaks up that end-to-end monolithic pipeline into three main parts. So you have what's called a feature pipeline that I've been talking about, and the feature pipeline can take data from real-time and batch sources and compute features. And in this case, you can see it's taking that input data and writing the features to the feature store. Now, feature pipelines can be run as batch programs on a schedule, or they can be streaming programs that are run continuously. And the features that are available there can be used for training pipelines. They typically run on demand. A training pipeline will take in input features and write out a model. And then finally, the inference pipeline, which takes the new features that are available, so the pre-computed features that are available for inference, as well as the model, need to download the model. And then maybe they might take some input data from an online application. They'll make the predictions and then return the results. So we can see here that the feature store architecturally will break up your system naturally into these three different pipelines that can all run independently at their own cadence, whether they need to run on a schedule or run continuously, or they can be run on demand. Now, for real-time machine learning, stream processing is a key technology. So stream processing is a technology which can process data in real time as it arrives, typically in an event-based form. You're going to have events of data arriving, and you'll compute features. Features could be, for example, if we're doing real-time credit card fraud prediction, we might want to know how many times this credit card has been used in the last 15 minutes. So you might have an aggregation, which is counting the number of times the credit card has been used over a window of time of 15 minutes. And that would be what we call a stream processing feature pipeline that would compute that feature. But feature pipelines in general, just to discuss them and to define what a feature pipeline is, a feature pipeline is really, it's a program that's going to orchestrate the execution of a number of steps, what we can call a data flow graph of model-independent data transformations, and the output's going to be features. So it's going to have some input data. These steps, typically it's structured as a data flow graph of computational steps. And the output is features that are typically what we call model independent. We want them to be reusable across many different models. And as I mentioned already, the kind of data transformation steps that you take that are model independent are aggregations, dimensionality reductions, binning, feature crossing. Dimensionality reduction could be computing and embedding on some data. And of course, other steps that you might take that are useful are validating your data. Maybe you have some missing data. You want to infer a data value, or you maybe want to exclude that missing data. But basically, the data wrangling steps that you typically would take in preparing your features for use in your application. So you can see we have this nice acronym just to help you remember the kind of steps that you take in the feature pipeline. We have the acronym VACE, where you have validate your data, aggregate, compress, and extract the features. So extract covers up many of the different techniques like binning and feature crossing that you would use. So that's feature pipelines. So if we look at how streaming feature pipelines can compute with input data, but also batch feature pipelines. In the streaming case, imagine we have a website and users are searching on the website. And we'd like to have a very reactive machine learning system that says, well, if I have, and let's take the example of TikTok again, the user has searched for some videos, or maybe they've been recommended one, they've been suggested several items. Let's say they've been suggested 4 different items. So the recommender system says, here's 4 items, and the user clicks on one of them. So that event will arrive at some sort of event bus. It could be Kafka. And those events will be fed into a stream processing program, and we'll call it a streaming feature pipeline. It's a program running on a stream processing architecture, And it's going to compute events. And the events could be, if we took the credit card fraud example again, how many times the credit card has been used in the last 15 minutes. It's not going to be much use here. So what we might want to, for the TikTok example, what we might want to do instead is each click that you make on a video, we're going to extract the category name for the video. And then we'll compute the counts over, how many different categories from how many different videos you have watched in the last, maybe we'll make it 30 seconds if we're going to be really reactive in the case of TikTok. And then our stream programming is going to run 24/7, and it's going to keep writing all of these updates. So as you click on films to watch and scroll, it'll update these counts. And these counts can then be used by your machine learning algorithm to say, well, what should I recommend? You've just been watching a lot of sports videos, or you've been watching a lot of music videos. I think, and a lot means in a very short window of time. So in the case of TikTok, it's obviously very reactive, but you can obviously extend those windows and have more than one window. You can have windows over longer time periods and shorter time periods, and you can recommend based on the near-term preference of people, what they've just been watching, and then also what they tend to like over a longer period of time. And then you can mix up and match those recommendations so that the users don't just get a very homogeneous set of recommendations, but that there's some variety in there to help them, maybe explore a bit more in their tastes. Now, you can also use batch pipelines. So these features do not have to be computed in real time if your application doesn't need, every 30 seconds to have a new set of features. It could be every 10 or 15 minutes, in which case maybe running a batch pipeline is more efficient or cost effective. So I've mentioned stream processing a few times, but I haven't talked about the technology for computing stream processing jobs. And the most popular frameworks out there today are Apache Spark Streaming and Apache Flink. They're both open source projects. They're both available in Hopsworks. So in Hopsworks, you can compute features in either Spark Streaming or Flink, and you can run it on any Flink platform. So you can run it on Amazon's Kinesis version of Flink. You can run Flink on EMR. You can run Spark Streaming on Databricks or on EMR. You can also run both Flink and Spark Streaming on the Hopsworks platform as well. It's your choice where you want to run these jobs. It is also possible to compute features if you're a data scientist and feel that, Spark Streaming and Flink, they're a bit heavyweight for me. I would prefer to stick to just Python because I feel comfortable and I feel I can be more productive in Python. And if you have very low volumes of data, you may consider using a framework like ByteWax, which is it's a Pythonic framework for stream processing. Under the cover, it's actually an implementation of what's called timely data flow in Rust, because Python-based stream processing frameworks are not popular because stream processing tends to be quite compute intensive, and Python is not very efficient at compute intensive jobs. ByteWax is kind of interesting because you can plug it into Kafka to recover state. So one of the key properties of many stream processing frameworks is that if the application crashes, they're maintaining state. So if you have the count of the number of times you've used your credit card in the last 10 minutes and a node crashes in a Spark Streaming cluster or in a Flink cluster, you shouldn't lose that state. So what they have is state recovery mechanisms internally where they can store their state. In our platform, both Flink and Spark Streaming can store snapshots and checkpoints in our file system, HopsFS, which is a HDFS API. So for those of you who are curious about Spark Streaming, it does need a HDFS API. You can't just plug it into S3. And Hopsworks works really well that way because there's this native HDFS API for HopsFS. So let's have a quick look at what stream processing frameworks offer you in terms of some of the core concepts and abstractions. And one of them is what we call windows. So I mentioned already that we might compute a count over a period of time, a window of time of 15 minutes. And these windows can differ very much. And obviously the aggregations that they offer are not just counts. You may have, a sum, you may have an average, you may have a min, you may have a max. There's a bunch of built-in aggregation functions. And in Flink and Spark, you can write your own custom aggregation functions as well. But the core of them are the windows. And intuitively, a tumbling window might make a lot of sense. You might say, okay, and if we continue with the credit card fraud example, we have a window of, here we have 10 minutes, and we count the number of times you use your credit card in that 10-minute period of time. And maybe you used it at minutes 10 and 9 and 8, and we have 3 events there and no events for the last 7 minutes. Okay. And then maybe in window 2, you used it at minutes 11, 12, and 13. So in this case, you've got 3 events in window 2, and it doesn't look like it's too much activity. But if you drew your window over the time from minutes 13 to minutes 7, well, now you've got 6 events in a 7-minute period of time. So that's quite a lot of activity. That might be more indicative of fraud, for example. So toggling windows, while they're quite useful for some examples, in that case, a sliding window might make more sense, where we don't have where the events would end up falling into more than one window. So if we had these credit card transactions, the events at minutes 10, 9, and 8 will fall into both window 1 and window 2. And in this case, window 2 would have captured the fact that there was 6 credit card transactions in a 10-minute period of time, which might be more indicative of a chain attack in terms of fraud on your credit card. So sliding windows are useful, and you can, of course, change the amount you slide. So these are configurable parameters, and they can slide with here we have a halfway between the windows we're sliding, but you can make those slides shorter or longer. You also have session windows in Flink, and the session window is useful particularly in e-commerce settings where maybe a user goes to a website, and when the user goes to this e-commerce website, they're going to search for things, they're going to click on things, they're going to put things in their shopping basket. And if you don't have a history of that user, the only features that may be available to you are the activity of the user during that session. So as the user browses your website and takes actions, all of these events should be sent to a platform like Kafka. And then with that user identity, which is maybe extracted from your browser, the signature you can compute from your browser, and then we'll be able to compute, for that particular user, we'll be able to compute some features. Not as many as if we had the history of the user, but maybe enough to help us nudge the user maybe to engage, or maybe to nudge the user to complete their the purchases in their shopping cart. There are also global windows available, so if you want to compute global properties over an entire e-commerce website, for example, then you can do that as well in Windows over a longer period of time. Now, many people who come to our platform are Python developers. We have a Python-centric feature store, and I did mention that Python is not an efficient language for stream processing, but ByteWax, for example, runs the code as in Rust in the Tiny Dataflow engine. Spark Streaming is very popular in Python, so PySpark for Spark Streaming. But as you know, Python is really the syntax, but the engine is a Java engine, so it's still quite efficient. Now, if we look at this example code that we have here, this is just showing you how you would use Spark Streaming in Python with Hopsworks. We can see that if we look at the beginning, we're able to read a data frame from a Kafka topic, and we're subscribed to a certain Kafka topic with a Kafka name. And we can deserialize the data from the Kafka topic to create a streaming query. In this case, we have a windowed query of 10 minutes. We're trying to get a signal from it. And I've omitted the actual select expression that we're going to look up, and we can see that we're windowing based on a 10-minute daytime window. In this case, we're computing rather than the count of credit card numbers, the average amount spent on a credit card over a period of time. But we can easily, if we want to change the count of number of transactions, we would have count here the number of transactions in that particular period of time. And there's something else called a watermark here. So in both Flink and Spark Streaming, it's possible that data will arrive late. So for example, if a website is temporarily offline and then the events get sent when the website comes back online, maybe due to a network partition, then the events may come and be late effectively for the 10-minute window from when they were produced. So the event time when the event was produced and when it appears in the window, it might appear 10, 20, 30 minutes later. You need to say at some point in time, well, let's stop accepting old data. And that's what the watermark does. It says basically, well, for data more than a configurable amount of time in the past, maybe 20 minutes, I'm just going to ignore it if it's that old. So we've got this windowed 10-minute signal data frame, and to get that data frame and the features created in it, this is the average amount spent on a credit card over a 10-minute period of time. To get it into the feature store, what we need to do is we need to have a feature group to write it into. In this case, we have one called card transactions 10-minute aggregates, and its version is number 1. And from this object, this feature group object, we just call insert stream on it. So we're going to insert this windowed 10-minute signal data frame into that stream. And with this query object, we can stop the query and check its status and so on. But you can see it's very straightforward code for computing a feature that can be run continuously. So this program can just run continuously in the background and continually take in new events arriving into your Kafka topic, compute these features, and write it all the time to the feature store. And from the other side of the feature store, then, your applications can retrieve those features and add them to their feature vectors and make the predictions. Now, that's stream processing primarily. The other types of features that we might want to compute in a real-time setting are what we call on-demand features. And an on-demand feature is where we haven't pre-computed the features. Maybe the application data is coming in the application request. Now, I'll stay on the topic of online fraud prediction for credit cards, because in that case, there is one feature that we have in one of our tutorials, which is called the Haversine distance. And what the Haversine distance is that when you make a credit card transaction, and then you have another subsequent credit card transaction in a geographical area that's infeasible. So maybe I use my credit card here today in North America, and then 10 minutes later I use it in Europe. Well, that's not physically possible if the credit card traveled in that period of time. So we might want to say that that's indicative of a geographic attack on the credit card. So the features we need for that are actually come with the credit card transaction. So when you use your credit card, you'll have the credit card number, the amount spent, the category of item that you're buying, but also the longitude and latitude of where that transaction happens. So the information we need for this Haversine distance or geographic attack will be the longitude, the latitude of the transaction, the timestamp of when it happened, and they only come in the application input. So in this case, if we look at what we can see on the slide, we have some application input. So for our credit card example, that data is going to come in here. And the way we can compute on-demand features in Hopsworks is with versioned libraries. So in this case, we can have a user-defined function. We call that a UDF, which defines our feature for computing the Haversine distance. We'll see it on the next slide. And we put that in a Python module. And this is our Python module here. And it's shared between the serving and then the offline training cases. So when we want to compute this feature, we compute it as a UDF in our serving pipeline, so in our inference pipeline. And we also use it when we're computing our training data, when we're creating our training data in the offline case. We're going to use the same function. We're just going to import it as a library, and that UDF can be used to, to apply to, for example, a data frame to compute the feature in the offline case. So let's have a look at that on-demand feature. So in this case, we have the Haversine distance, as I mentioned, and you can see it takes in longitude, latitude, and then the previous longitude, previous latitude. And then we'll also need the timestamps, which are omitted here for brevity. And what we can see here is that this is just the feature logic then to compute the feature, the Haversine distance. There's a couple of things we need to think about, right? So in the offline case, the input values may actually be a pandas series, so we can do a typecast from our primitive type to the pandas series at this point. If it's in the online case, we're using this function, then we can keep the primitive values and just compute them on the individual input here. So you also may notice that previous long and previous lat, this is historical data. So where do we get that from? Well, we need to go to the feature store again to retrieve the most recent credit card transaction and get the previous long and previous lat, because that won't come in the input data. Okay, so that's an example of an on-demand feature, and again, the technology for doing this is really just to define a Python UDF, have it versioned, and it's distributed in your online inference infrastructure, in this case in Python, and in the training infrastructure, again, in Python. So it could be Pandas or Spark. So I've mentioned the credit card example a few times, and this there is an online credit card fraud tutorial that's available on our website. And when you register at hopsworks.ai, when you create an account, we have the serverless platform there when you register an account on Hopsworks.ai and you come into the serverless feature store, you'll notice there's a number of tutorials, and you can try out those tutorials. One of them is online credit card fraud, so you can get started. So just to summarize, we've looked at Hopsworks as a platform for doing real-time machine learning in the case of what we call operational machine learning. Data comes in real time into our feature store, and it's used by online applications to make low latency decisions, to adapt to changes in their environments quickly, and give quick feedback to users about maybe events that are of interest. The other part of Hopsworks that may be of interest is the model serving is also included in the online platform. So if you want to try out the service version of Hopsworks, there is built-in support for what we call K-serve, so you can easily put together a POC covering not just the real-time feature engineering, but also the inference pipelines in the platform. And it has a time unlimited free tier for you to get started with. So you'll be able to run at least 2 models concurrently in that inference tier, and then you can serve a number of feature groups online to get you started today on Hopsworks. So go to hopsworks.ai. There's their public Slack as well, where you can get help in our community. And please reach out to us to ask any questions. Thanks very much.